Hello, everyone. Thank you for joining the Sentinel Power webinar today. Today's presentation will be presented by James Hofmeister and Robert Wagoner. James Hofmeister, also known as Hoffy, has been starting these webinars a few months back now, and he's covered a CBM Plus and a PHM system architecture. And today we'll be going into Sentinel Power, which is another family member within Sentinel Suite. So he'll start off the presentation, and then Robert Wagoner, the Senior VP of Product Development, will join in during the Sentinel Power software demonstration. Thank you for joining us.
Good morning. The agenda for this webinar is we're going to introduce Sentinel Power. We're going to briefly discuss the development history of the Smart Probe, which stands for Sample Mode Response Technique. And we're going to do a demonstration of the current version of Sentinel Power, working with the current version of A-Rule. Then we're going to discuss our new A-Rule 2.0 and what we're going to do to improve Sentinel Power to take advantage of the functionality of A-Rule 2.0, which is fast convergence, signature transforms, and improved flexible modeling, fast and accurate prediction estimates, prognostic horizon, multiple nodes, and checkpoint restart. Checkpoint restart supports the non-24/7 monitoring. That is, you bring a system up on Monday, and Monday afternoon you turn it off, and maybe next week you power it back up, and you would like your system to resume where it left off. Then we'll do a summary and take questions and answers. Next.
And I do want to ask everybody, if you do have questions, to save them towards the end, and we'll address them at that time.
Okay, that's very good. Today's seminar is a continuation of the PHM framework. A framework, what we refer to as a framework, and also the PHM Society and the ongoing PHM Standards Committee. You have a sensors framework, you have a feature vector framework, which is basically signature and data processing. You have a prediction framework. You have a control and data framework, which controls the flow of data from a sensor to signature processing to a prediction, and then the forwarding of prediction information to a fault management framework. Some of these frameworks, of course, the lines blur somewhat because some function is done in a Smart Probe, for example. So other functions are done offline in a batch mode processing. Next. Sentinel Suite. Sentinel Suite consists of several towers, if you will. Last seminar, we discussed Sentinel Motion. Today, we're going to discuss Sentinel Power. Sentinel Suite is a family of advanced sensoring, monitoring, and diagnostic solutions based on Richtop's group's condition-based maintenance and prognostic health architecture, sensors, and other processors. Sentinel Motion, which is a previous Sentinel, was primarily to monitor electrical mechanical systems, aircraft infrastructure, for example, the gearboxes, wind turbine, and other like equipment. Sentinel Power is to analyze and diagnose power systems, primarily those that have a rectification from AC to DC, DC to AC, back to DC, and have a filtering circuit. Future seminars will discuss Sentinel Interconnect and Sentinel IT. You could think of a condition-based maintenance PHM system as a part of an ecosystem. You have Sentinel Suite there as number 2. It's taking data from number 1 from a bunch of sensors on some vehicle or some site. It processes that data. It produces information about the state of health and diagnostic information, which can then be used going downward for real-time maintenance and scheduling of maintenance, and also to say, well, this particular component is failing much faster than I would like. Perhaps I need to improve my design. And you can also use that to minimize your inventory by saying, well, I'm going to need to replace my power supply within 30 days, so I'll need to schedule maintenance in 15 days, so I need to make sure that my power supply is available in 15 days. Next. What is Sentinel Power? Put it in a nutshell, Sentinel Power monitors the output of a power supply. And a power supply is very noisy, as illustrated in the upper right-hand corner. It has many types of noise. All noise can be basically used for diagnostic purposes and for PHM purposes. You have droop, you have a damp ringing response, harmonic distortion, ripple voltage, thermal noise, and you have switching spikes and glitches. All of those can be used as feature data, and when it's used as feature data, it's important for a particular diagnostic or prognostic purpose. Everything else is noise. We use patented power signature monitoring sensors that we've developed, and we have patents on it. We have advanced prognostic reasoners, and we have a Sentinel PowerView software. This solution monitors your mission-critical power supplies, and we observe a range of failure modes. Some of the modes that we here at Richtop have looked at and for which we have solutions in-house, some of those we have externalized, some we have just kept in-house until someone wants them from us, is loss of filtering capacitance, loss of gain in the feedback loops of a power supply, loss of phase margin, loss of filtering inductance, loss of effective parallel resistance. Those losses are commonly referred to as failure modes. Failure modes produce very characteristic signatures. For example, a loss of capacitance in a filter circuit will normally produce a signature that looks like a square root function. A pi filter will normally produce a filter that looks like a convex increase in current or increase in noise. So those are very characteristic signatures, and we have identified 7 such families of signatures. Next. From a very simple point of view, you have a what we call a prognostic target, a monitored power supply in this particular case. You have a sensor. A sensor our smart probe looks at the output of it. The sensor produces data which goes to a PC program, or a PC host, if you will, and it's running Sentinel PowerView. And off on the very far right is a damped ringing response that we look at with our Smart Probe 4000. The damped ringing response consists of an amplitude, a resonant frequency, and an exponential decay. All 3 of those features or sub-features can be used for prognostic diagnostic purposes. Our Smart Probe, we're looking at frequency. The Smart Probe voltage analyzer, that's another type of sensor that we have to look at power supplies. It is offered as a 1 or 2 channel sensing device, and it primarily looks at the output voltage level, it looks at the noise, it looks at the AC components, and to detect instability, excessive ripple voltage, and harmonic distortion. Next. Sentinel PowerView is a software application that processes data. For example, on the very top screen, you can see the frequency that we expect. That's the dark orange. The light orange is a frequency that we're currently detecting. At the bottom is the signature that we're looking at, the curve, if you will, and the third waveform is state of health. It provides a graphical user interface as opposed to a command or end user interface. And all of our Sentinel View type of processors look at feature data, pass it to for further processing, and to come up with a state of health. It manages the control and data flow, as we mentioned before, between the Smart Probe sensor, our prediction engine, which we call ARU, and a PHM system user. Next. Richtop, we use a standard set of approaches and methods to come up with a solution. We look at what the problem is, and we do modeling, we do simulation, we do experimentation, and we do feasibility studies. We use physics of failure analysis, we do failure mode effects analysis, and between those first three, we say, aha, this failure mode that we're trying to prognostic enable will produce this kind of characteristic signature. We can capture that signature by these methods, and if we do so, we can then provide a diagnostic PHM solution. We then do, we build test beds, we build simulation engines, we do testing, we evaluate, and then we select which solution approach we're going to go forward with. Smart probe development history. It's been a long history, and we're just going to do a brief summary to give you an idea of the solutions that we have in-house and the solutions we're offering with our software and hardware. This is a typical output. This is an expanded view of what we've seen before. Every one of those, ideally, a DC power supply will produce a DC voltage without any noise whatsoever, no droop, no ringing responses, no ripple voltage, no harmonic distortion, no switches, spikes, and glitches. This flat. But that's not the real world. The real world is you have droop, you have ringing responses, you have all of those noise in your output. The goal of the designer of the power supply is within the cost that his budget is to design a power supply that produces an acceptable level of noise. Next. So what is an example of what we do? We take this this example power supply and we say, okay, it's got a pulse width and or a pulse frequency modulator. This is one where we're taking AC or DC input, we're converting it to an AC, and then we rectify it and we filter it to produce a DC output voltage. And then we have a feedback. That very simple diagram, when you look at it, you may not realize it, but this is the way it is. This is the real world. The filter is subject to failure of capacitors and inductors. There are other failure modes, but those are the common ones. The bridge or rectifier is subject or prone to failure of the power switching transistors, sometimes the gate drivers and the amplifiers, but primarily the gate drivers and amplifiers are due to problems with the pulse width, the pulse frequency modulator. The feedback, a common mode of failure in the feedback loop, is the gain of the amplifiers in the feedback loop. Next. So, this is some of the failure modes that we here at Richtop have looked at. We've looked at a leakage current. That's a failure mode associated with a decrease or increase, if you will, of the effective series resistance. When I say increase, what I mean it becomes less efficient. Loss of gain, that a typical mode of to detect loss of gain is to look at the ringing decay and also the amplitude of that ringing. Loss of inductance, ripple voltage, loss of filtering capacitance, you can look at ripple voltage. Loss of capacitance, to some extent, inductance, you can use resonant frequency. Loss of gain and feedback, distortion and instability. Because when you lose gain in your feedback loop and you begin to lose feedback inefficiency, with it, for example, a decrease in Miller or capacitance feedback, you typically shift the phase margin of the power supply, which results in distortion and also in unstable operation. You can also look at a power switching transistor. Typically, we don't use or try to prognostic enable power switching transistors because when they fail, it's almost avalanche type of failure. It happens very quickly, and it's sort of like, well, it's going to fail in 1 second. So from a PHM point of view, that's really not a eligible target. Next. Leakage current. We looked at this and we used a direct measurement to measure a leakage current, and it worked. But we decided that, yeah, that's a little bit invasive because you have to actually disconnect connectors and put a meter in line with it because you can't use an inductive or capacitive pickup because the leakage current is so small. Furthermore, leakage current is typically associated with electrolytic capacitors, which have a high failure rate. If you use metallic oxide capacitors, it has a much lower failure rate than electrolytics. But more importantly for us is that mill space applications don't use electrolytic capacitors. So therefore, this was a non-starter for us, and we decided to not go forward with an external solution. Loss of gain, ringing amplitude. This at first looked very easy, and said, well, we can measure the initial amplitude of the ringing response, but we found that it was difficult to measure because of noise, switches and glitches. And furthermore, the loss of gain was typically associated with an optocoupler amplifier. An optocoupler is used not only for gain, but it takes the place of a transformer. It's got a high failure rate. Today's modern power supplies use solid-state amplifiers, which have a much lower failure rate. But most importantly, again, from our point of view, mill space applications don't use optocouplers. Next. Loss of inductance and capacitance. We looked at ripple voltage. It worked very well for capacitance, a little bit less reliable for inductors. But we said, well, that's a problem. But then we decided that the inductor failure was related to failure of the power switching devices, which were often related to a loss of filtering capacitance, i.e. a short. So the short would occur, the transistor would then try to drive infinite current, which would then burn out or severely damage the inductor. But most importantly, we found that ripple voltage is greatly dependent upon the variability of the power loads that the power supply is attached to. So the solution, ripple voltage, is very good for bench testing, but not good for in situ monitoring. So we decided not to go forward with that solution. Loss of capacitance. When we did the phase of failure analysis, we said, you know, when the capacitance changes and or the inductance changes, the resonant frequency will change. And we did experiment and we verified that was so. And we said, well, don't we still have a dependency on the load? No, because typically these power supplies or expensive power supplies are designed to be high Q. And when there's high Q, you basically have a square root of 4 over times the Q. So it's very much reduced, a negative factor. So this is a very good solution for high failure rate of tantalum oxide capacitors. When we say high failure rate, tantalum oxide capacitors per se have a low failure rate, but they have a high effective series resistance. So mill space power supplies use a whole lot of capacitors. For example, 22 tantalum oxide capacitors connected in parallel. So even though the failure rate is low, as a parallel configuration, they have a relatively high failure rate. So this is very good for us. And this resulted in our Smart Probe 4000. Next. Another one was loss of gain and feedback efficiency, basically distortion and instability. We came up with methods that could detect and quantify distortion. We could detect and quantify instability. And we could detect and quantify changes in ripple voltage amplitude. And we use those three to calculate a composite figure of merit. If it's below a threshold, the power supply is considered healthy. If it's above the threshold, it's not healthy. Somewhere in between, it's sort of questionable, maybe good, maybe bad. This turned out to be a very good, useful diagnostic. So we went forward with what we call the Smart Probe VA1000 and the Smart Probe VA2000. The difference between the two is VA1000 is a single channel and VA2000 is a dual channel. Next.
Okay, so now we're getting to the Sentinel Power demonstration section of today's webinar, and it will be presented by Robert Wagoner.
Oh, thank you, Hofi. So when we did this, we wanted to also make an end-to-end low-cost demonstration, and so we sourced a off-the-shelf PC power supply, removed its capacitance, and then built a programmable capacitor called PCDD, Programmable Capacitance Degradation Device. We coupled that with the Sentinel PowerView so that we could show a full condition-based maintenance, highly accelerated scenario and show prognostics with state of health and remaining useful life. And you see in the diagram there, we have the smart probe and the PCDD and then the power supply. And we'll give you a even more accelerated demo that was summed up in a 30-second video. And you see at the top bar there, the Smart Probe 4000, you can select, you can log various iterations, and you can degrade it at different percentages, and you see it's degrading from 100% down to 0. Frequency is increasing, indicating the loss of capacitance. And so this customer demo or sales rep demo is a very good on-site 7-minute demo that really gives you an end-to-end prognostics. And next slide. So Hofi's explained these, and we see that the Smart Probe is a signal processing unit that captures this information in a very parasitic way. It does not cause disruption to whatever the system is being powered. It's very convenient to have multiple of these units. You see the signature there, amplitude and over time, part of like the bathtub curve. Next slide. And here we see the prognostic signatures over time. Gives you the estimated remaining useful life, and you can select these particular areas as warnings and alerts to get ahead of your condition-based maintenance schedules. And next slide. And as Hofi was explaining, you have a really good example here with the VA probes of what a good signature looks like in samples, and then you have a distorted, harmonic distorted signature that we detect and likewise can provide warnings and alerts. Next slide. And here's some more clarifying plots of what's expected, nominal system, and a detected. Abnormal could be anomalous, but all these signatures are provided as outputs through various smart probes.
And Robert, may I interject something right here?
Sure, sure.
Yeah. What we do is we expect, as you can see on the upper left-hand corner, and we know that when and because we observed it, when the power supply is right on the verge of going into the positive range on a phase margin because of loss of gain and Miller capacitance, it begins to break up into oscillations. So you get something that looks like the output on the upper right-hand side. We also know that in addition to instability oscillations, we get harmonic distortion. Instead of getting nice, relatively clean sine waves, we get something that looks like they're in the middle row on the far right. We process the signature in different manners, and our methods, we produce what we expect to look like on the lower left. That's what we expect. Because of instability and or harmonic distortion, we will get something that looks on the lower right-hand side. And so we're able to quantify those two values and say, well, this is larger in amplitude than we expect. Okay? And we do that for the 3 modes, and we come up with a composite figure of merit.
And that's what makes it a very useful diagnostic tool, correct?
Okay, yes, the Sentinel Power Development Kit we provide with a GUI, a standalone hardware component, and various licensing agreements. And we also can do design services for on-site and remote training and consulting. So just ask your rep or call us directly.
Alrighty, thank you, thank you, Robert and Hoppy, for joining in on that section. So we'll continue today's webinar going into the Prognostic Reasoner, A-Rule 2.0, which is a key component within Sentinel Power.
Yeah. We here at Richtop don't like to sit on our laurels, and even though we have a very good Prognostic Reasoner and PowerView, as demonstrated by Robert, we've gone ahead and we have improved A-Rule. Through our use of A-Rule, we observed that there were certain things that we felt could be made better, which could be improved and could be made more accurate. If you look at, we started off with that framework, which had basically on the left side and on the bottom, the sensor framework, the feature vector, and the prediction framework. We found or discovered that in reality, the feature vector and the prediction frameworks are very closely tied together. That if you do your feature vector correctly, it makes the input into the prediction framework much better for producing accurate diagnostics. So we changed and came up with the architecture you see on the right-hand side, where instead of two frameworks, we have a single A-Rule engine that performs the function of the feature vector framework and the prediction framework. The input, we've simplified the interface, so we produce a input here, as you can see on the lower left plot. Those signatures are typically power curves or exponential curves. And we have devised a method where you can tell us the basic kind of curve that your signature looks like. We will then do internal transforms, and through our using various things like particle filtering, Kalman filtering, random walk techniques, trending, etc. We will take curvilinear data like that and produce a prognostic horizon, which ideally is a nice horizontal straight line, remaining useful life, which should go from the right where it starts to degrade. That amplitude, say it's 100 hours, it should be equal to 100 hours later, it should fail. And that's ideal. And then we produce state of health. We have found that state of health as a measurement is always, with our engine, extremely accurate. Almost always more accurate than remaining useful life. And that's why in the plot that you saw that Robert produced, he chose state of health instead of remaining useful life, because that is in fact more accurate than RUL. Our new engine, A-Rule 2.0, amongst other features is fast convergence. As you can see in the middle plot on the right-hand side, no matter what it is, you cannot accurately say it will fail in exactly 100.5 hours. You're either going to be high or low. You'll never be right on. So our engine has to start with an initial error and converge to the true solution. And we do it very, very rapidly. We do signature transforms. We have very easily modeling. It's extremely accurate, and it produces RUL plus SUH to give a prognostic horizon. Prognostic horizon is a metric that we here at Richtop invented and added to the repertoire of PHM terms. Next. Okay. We also can take a architecture, and you can have node-based, you can have it process-based, you can have it feature data-based, but we feel that node-based is the best, because if you think about, for example, a tank has many nodes. It has many LRUs. It has an engine, it has a transmission, it has some rotors on the wheel assemblies, for example, it has power supplies. Each one of those can have more than one sensor. So each line replaceable unit becomes a node. Each sensor attached to that node becomes a data node. So this is the architecture we come up with. It says you have one or more system nodes. Each system node has one or more node definitions. The node definition basically says, what is the characteristic signature that I expect from this sensor? Okay, so, and then it also says, the input data set is here, it's located in this directory, it's got this name, and I would like the output to go to that directory with that name. We also have a special directory, what we call checkpoint restart. In the real world, you cannot monitor a set of nodes 24/7. It's totally impractical. Your system goes up and down. The thing you're looking at is active and becomes inactive, so it's starting and stopping. But what you would like to do for prognostics is when you're processing data, is to say, the last time I looked at the data, 45 days ago, it had this value. So you have to save that information and recover it when you do the next data point. Next. We use that architecture, and we've blown this up so you can actually see what our engine does. Our engine takes data, one data point at a time, and each data point, when in a total, forms a characteristic signature. We take that data point and one data point at a time, we transform it from featured data to fault to failure progression signature, FFP, then to data progression signature, and then to functional failure signature. We do that on a data point by data point. We do not do curve fitting. We then take the result, the FFS, functional failure signature, and we feed that into ARUL, the engine. That's a prediction engine. The prediction engine has convergence algorithms. It has common light filtering, random walk filtering, particle filtering. It has learning methods, and it produces RUL, state of health, prognostic horizon, and other information that can be of use to prognostic enable a system. So, ARUL is talked to or has an interface, what we call an application programming interface. You've probably heard that term before. You have an application-specific program. You have our ARUL engine. The API has external parameters and values, internal variables and values, and an I/O bus. That API is how you communicate with our ARUL engine. Next. This is a more detailed view of that. You have an application program. A typical application program does initialization, housekeeping. It needs to set up the API and the input-output buffers. Then it needs to get a data point, put that data point into an I/O buffer, and then give that data point through the API and the IOB to the ARUL engine. The ARUL engine then comes back with updated information, which the application program can do selective data verification. For example, it can look at the data and say, oops, I need to initial alert, or oops, the unit I'm looking at has failed, or it's healthy. So it does some selective data verification and processing of the data. Then it needs to write and build an input-output buffer and save that data away for future processing or for historical purposes. This is an example of a system node definition. It defines and it points to the CPT library and the node definition, the sources of them. And you can see it's very general in form. We have presented this so that it can be easily processed using a very simple BNF, Backus normal form. Right there at the very first 3 lines, you'll see the definition or set up for a checkpoint restart library. Then it defines 2 nodes. The first node, the input, the node, where the definition of the node itself is that directory with that data set. Node number 2 uses, in this example, the same library, but a different source data set. This is an example of a node definition. And on the left-hand side, you'll see that the node definition consists of the external parameters and values that you feed into the A-rule engine. What we're going to do for, in our example is, we're going to show as comments, basically a line that begins with a percent sign, and that's the form that we're using for comments. And we will show as comments all the defaults that the A-rule engine accepts. And then we will only show, for our node examples, those parameters and values that we have changed. That makes it much simpler so that you as a user can say, aha, I've got this API, it's got all these 20 some odd variables and parameters, but in reality, I don't really need to worry about them because they have default values. The other side, on the right-hand side, those are dependent parameters having to do with the node itself. For example, what is the input file that the data has been kept in? What is the output file name you would like? Do you want me to write it to an output? For example, if you haven't specified a required value, do you want us to ask you for an option, or do you want us just to go ahead and pick a default and do it? Do you want us to write, or do you want us to ask before writing, overwriting a file? What type of is your input file? Is it a .txt file, or is it the .comma separated variable file? We allow you to pick and choose. We allow you to pick and choose the prefixes and suffixes that we look for. Down at the very bottom of interest to you is the fact that there are alerts. For example, the AH99 says, issue an alert whenever the state of health falls below 100. Issue an alert at 75, 50, 25, 10, and functional failure. Next. Okay. What is, or how do we deliver A-Rule 2.0? The engine, we deliver it as C executable only, but the API is an open source API. It is fully documented. It will be fully implemented in Sentinel PowerView. That's what we're working on right now. And it will come with an installation verification procedure to allow you to verify that you have correctly installed the engine and all the parts needed to run it.
And Hofi, just as a general note, if I may add here, so this capability is what gives a PHM system, an existing PHM system, the capability of adding this prognostic algorithm to it.
Yes, you can. That's a very good point, Wyatt. You can use our A-Rule engine for your own prediction engine, in addition to or in lieu of. You can also use our A-Rule engine as is, because we're going to also show you an application that we're going to provide to you, or you can develop your own system around our engine.
Correct.
We will deliver a test bench. This test bench is data specific. It calls our A-Rule engine. It will be delivered in executable form and also in source form. The source form is allow you to assist you in determining what you have to do in order to communicate with our engine. And we're not saying that this is the only way. The test bench is provided as an example. This is what we did to talk to our own engine. It processes A-Rule output. We have a second program, we call it an example evaluation program. It processes the output produced by the test bench. It also is delivered in executable and example source code, again, to provide you with a hint or assistance in developing your own application to determine how well A-Rule and your application did or did not do. We're also going to provide a third deliverable that comes when you order A-Rule, and that is an example data application. It reads user data sets, and we will provide some example data sets. And these data sets will have different kinds of signatures. The idea is, rather than you taking the time and effort like we did to evaluate what the signature is it a square root curve, or is it a power with a power exponential of 0.45? Rather than having you do that, we will provide examples, and all you need to do is say, yeah, my curve looks something like that, and so I will use that template to process my data. We will deliver it in C executable and also example source code, again, to help you in developing your own method of talking to our engine. The API, again, is the open source application, and it calls our A rule executable. Next. Okay, message and alert. At the very top there is an example of a log file that this user program produces. You can see that on the 3rd of August, in a test case I was running, it was an invalid keyword in the node definition, and we detected it, and we issue a log to the message to help you in diagnosing problems with your definitions. Then on the 5th of August of this year, you can see that we had an error opening the system node definition file. That was the directory, and that was the file. And what it was there is I happened to be looking at it, and I hadn't closed it. So when I ran this program again, it said, I'm sorry, the file is busy. So it could not open it for write because some other application had it open. And these are examples, again, of alerts. I just happen to pick, issue an alert, no alert, issue an alert, no alert. But you can choose. You can feel free to choose any value you wish to. You can also set up your own values. Today, we focus on the sensor framework, the smart probe sensing devices. We focused on the control and data flow as exemplified by our Sentinel PowerView software application. We focused on the feature vector framework and the prediction framework. Those two frameworks, we have collapsed them in the new A rule into a single two-stage engine, which simplifies the control and data flow. It also simplifies how you talk to and use A rule. We spent a lot of time on physics of failure and FMEA. Those are two very important common methods to diagnose data and to determine what does my signature look like, what effect does the failure mode have. You can, for example, measure the water in a tank to determine whether or not the temperature in your house is correct. You have to select a sensor to match the failure mode. And if the failure mode is evaporation of water, then you need a different kind of sensor as opposed to a failure of a heater if you're heating the water. So physics of failure and FMEA are very important approaches and methods used in prognostic enabling. Then we discussed an overview of our significantly improved A rule prognostic reasoner.
All right, so thank you, Hofi, for joining us and giving us a great in-depth overview on A rule as well as Sentinel Power. So if there's any questions at this time, I'd like to invite them open. Feel free to use the chat feature, or we can open it up for discussion now.
Questions?
So what's the sample rate? What's the sample rate you're using for the data?
I'm sorry,
the sample rate for the data?
In our previous seminar, we talked about the fact that your sample rate, there's really two modes of sampling. There's the low sampling rate, such as once per hour. And then at that once per hour, you typically sample in a burst mode. For example, if you're looking for frequency in the range of 25 kilohertz, you don't want to sample 50 kilohertz, minimum Nyquist criteria, would be twice that. You don't want to sample at 50 kilohertz 24/7 once every second. You don't have enough bandwidth. You don't have enough data storage. So you sample at a lower rate. What rate is that? Well, it depends. It depends upon what your accuracy is. If supposing, for example, let's take a typical military application where the general says, I want to know failure at least 72 hours in advance, and I want to know in terms of plus or minus 1 hour with an accuracy of 10%. Well, okay, so I'm going to sample once a week. Oh, no, you can't do that. If you want to know plus or minus 1 hour, that means you have to sample at least 4 times an hour. Okay? Then it's, well, okay, you want 10% accuracy. Well, is that 10% accuracy of what? If that's 10% accuracy on your plus or minus 1 hour, that means you have to sample 40 times an hour. So the sample rate and the burst mode depends upon the accuracy requirements of the system.
So how much historical data is needed? Like you were talking about, like how you store historical data. How much is actually needed for the system? What's that dependent on?
Actually, we have a lot of historical data, and you don't need very much, because if you think about it, for a given failure mode, the signature is always going to be a square root or a square curve, always, or a cube root type. It's not going to change. The only thing that's going to change is the rate of failure. Okay? So we look at characteristic signatures. The job of the engine is to detect how fast or how slow is the failure rate compared to what I was told the failure rate was, and it adjusts its internal model accordingly. So the sample rate, we don't need much. All you really need is about 50 points and 1 data set. And that should be enough to say, this is what a curve looks like, and you use that and say, yes, I can verify that I have selected the right curve and I have specified the right exponential value or power value. That's been our experience.
Awesome. Thank you.
Okay, Hoppy, so I had a question. We talked a little bit about the Pareto ranking of the failure modes in Sentinel Power. The loss of capacitance and inductance is a predominant failure mode, correct?
It's primarily the capacitance, at least for mil spec. Because what happens in the military type and space type applications, they use metallic oxide capacitors for dielectrics. And those have a very high effective series resistance. So they put a whole bunch of smaller capacitors in parallel, okay, so that the total capacitance satisfies the power delivery that they require. If you recollect that current is basically dQ over time, and dQ is a function of capacitance and voltage change, right? C over dV/dt. So they design it, and they say, I need this much capacitance. I'm using a metallic oxide. It's got this much series resistance, 10 ohms. Oh, that's too high. I need to get it down to 1/10 of an ohm. So what do? They connect 100 capacitors in parallel. Okay, now the power supply has been charged up, it's running, and then it powers off. Well, you've got 100 tantalum oxide capacitors in parallel. And it's got to drain the charge to the bleeder resistor and also through the capacitors. So what happens is one capacitor will have a significantly lower ESR than the others. So most of the current will drain through that capacitor. So that capacitor has a tendency to overheat. When it overheats, it basically damages the dielectric, and then it begins to short. So the common failure mode of metallic oxide capacitors in a parallel filter circuit is one of them will fail short, and then it burns open. Your power supply is stripped off. You turn the power supply back on, and now you have 99 instead of 100 capacitors in parallel. You test it, it tests fine. Everything you measure will be exactly within specs. And so on and so forth, all the way down to maybe 20 capacitors before you begin to notice that you got excessive ripple voltage. By that time, you have invariably damaged your switching transistors, because your switch mode and your pulse frequency modulators will have overdriven the gate drivers to the power switching MOSFETs, which cause them to overheat, which damages the crystalline structure, which damages the transistor.
Okay. And this iterative process of losing capacitance due to failed capacitors and that type of circuit is diagnosed with our Smart Probe 4000. And is it possible to equip a power supply? So that's a prognostic sensor that we have, right? Is it possible to equip a power supply with the diagnostic capabilities as well with the Smart Probe VA?
Yes. As we talked, the Smart Probe 4000 will detect a frequency change associated with capacitors. But what we found, especially with solid-state inline voltage regulators, for example, typically the manufacturer of an inline voltage regulator, which is a type of power supply, will state that the output photocapacitance ranges from nothing to 50 microfarads. Well, so you go over there and you connect your power supply to your load, and you have no capacitors in it. The manufacturer said you didn't need any. And your download requires 1 amp. Without that photocapacitor, you basically have to run. And these inline regulators are basically constant current, so they have a very high frequency, a refresh frequency. It's not 400 hertz, it's more like 2 megahertz or higher. So it's a constant current. It overdrives the gate drivers, amplifiers, it overdrives the power switching amplifiers, and therefore it damages the crystalline structure, the gain is reduced, the feedback, the Miller feedback capacitance is reduced, and you get distortion. And our Smart Probe VA detects distortion. Because what you want to do is say, even though this power supply is producing 3 volts or 5 volts, and even though it's capable of driving, delivering 1 amp of current, which is all I need, that power supply is damaged. And it's got very high frequency component. It has a tendency to break into oscillations, and you surely don't want to use that power supply in your aircraft or your space vehicle.
Okay, thank you, Hofi. So we'd like to open the floor up for any additional questions at this time. Hans, I do see that you're online. You're welcome to shoot off any questions that you may have.
Hi guys, good morning to you. No, I have, for the time being, no additional questions. So I would like to congratulate you for a well-run webinar, and I hope it's getting a good traction after all.
Yes, yeah, so we will be sending out the slides to all of our registered attendees, and we'll also post the recording to our YouTube channel. We also have overseas reps that'll have access to this, and they'll be sharing that with their contacts and customer base. So for the time being, it looks like we've captured a lot of good content in a short duration of time, and I'm thankful that technology still allows us to interact and engage with our customers. We're still doing great engineering here. So thank you everybody for joining us, and we'll be concluding today's webinar.